Hello everyone, welcome back to this amazing session. In this session, I'll be discussing about unfolding, a very easy topic on the fifth module. I have a textbook over here which I'll be using to explain what is it actually. So basically, if you can see here, unfolding is nothing but it is a. So first, we have to talk unfolding computational graphs, right? So there are two things. One is unfolding, one is computational graph. What we are unfolding this computational graph. First, let us understand what is computational graph. It is nothing but a way to a graph which formalizes the structure of set of computations. In this graph, it will be showing us how the inputs are mapped to output and how the parameters are mapped to the loss and all. So that's what it is. See the definition. It is a way to formalize the structure of a set of computations such as those involved in mapping input and parameters to output and loss. What is unfolding? It is the idea of expanding recursive or recurrent computations into a computational graph. So now what we have to expand over here, we have to make this recurrent or recursive computation into computational graphs. You have to expand it such that it has a repetitive structure. Okay, so computational graph will have a repetitive structure, which we'll see in the diagram. Okay, you can see as a repetitive structure. This typically corresponds to a chain of events. If it is repetitive structure, then you have a chain of event. Then also unfolding this graph results in sharing the parameter across a deep recurrent structure. So we can see over here, leave that. We will talk directly about the basic dynamical system. You have to talk about classical dynamical system. After the explanation, you have to talk about classical dynamical system and write this formula. If you can see here, it is highlighted over here. If you cannot see, like if the tab sharing doesn't record completely, I have written over here exactly. This is the bracket. Okay. So what is S of t here? It is a state at time t. So then f is what? It is a transition function. Theta is a parameter which is shared across time. Same function every step. Why this is recurrent? Because to compute st, so if you want to compute st, then you have to compute st minus 1. And then if you have to compute st minus 1, then you have to compute st minus 2. Okay. Unfolding for time steps. So now we'll take a finite number of steps. We don't know what is t. So if t is 3, then what will happen? We have to compute s of 3. F of 3 is equal to nothing but f of s3 minus 1 theta. 3 minus 1 nothing but what? 2. So then we have to compute s of 2. What is s of 2? It is nothing but f into s of 2 minus 1. That is what? 1. S of 1 theta. Now we have to substitute this 2 into 3. What will happen? S of 3 is equals to f into, in place of s of 2, you just have to write this whole thing. See, this whole thing will be written in place of s of 2. Then it will be shown as what? F into s minus 1, I mean f into f of s1 theta, then again one more theta will come. Okay, because if you see here carefully, this whole thing s2 itself has one theta over here, so you will have two theta. This is also a theta over here, so it will include again. Understood, right? So basically what is having now, if I write f of 2, so I'll write s2 here, f of s1 theta. This should be substituted in the place of s3. So s3 is equals to f of, now in the place of s2 I have written this s2 over, then like this, theta. Okay, very simple. Now there is no recurrence in the expression. This is just a composition of functions. So now figure 10.1 shows what? See, same chain s, so on up to some particular number. Then here basically s t minus 2, t minus 3, so on it will be there. T minus 1, just add plus 1, that will become t. T plus 1, t plus 2, so on up to 1 and 2, it will become s. So here at the end you will have s1. Okay, here you might have s minus 1, something like that. Okay, so here every arrow uses the same function f. See, every arrow uses the same function, transition function f, with the same theta, same parameter theta. So see, that is the nothing but recurrence. So here parameter sharing and all happen. Then this is the heart of a deep graph created by repeating the same block, adding the external input sign. So now what you are doing, instead of just s of t and theta, we are introducing x of t, like this. Okay, you can see in the textbook over here. Over here it's written over s of t. So now where did it go? Yeah, the system is driven by an input xt. So now if I just mention it, now in RNN notation they rename state st into hidden state. So what will happen? Usually in RR, so the state s of t will be renamed as hidden state, that is h, hidden state. So now you have to replace h, s with h. Simple. So wherever s is there, you just have to mention h. That's it. What is practical means, at each time step you read the new input x, you combine with the memory h t minus 1 to produce or update the memory ht. Simple. So we will use the input xt for a memory and combine with the memory ht minus 1, so with the previous state, so that they can produce the updated memory. If I have to show in the diagram, see here, xt is using the previous memory to produce the or update the current output state. Okay, so see, this is like that. Okay, so previous memory is used, and basically see, this arrow mark is will confuse you. Basically what is happening, this input is used and this output, so what is the previous state is coming here. So see here, ht is having two incoming arrows, one is the previous memory and one is the input, so they both are combined to give us what, xt. Okay, it's just like that, understood, like understand like that. So here, this thing, what is happening here, you have one function f, you have head state, then you have input x. So here you can see a self loop. So this is a time step. Okay, so we'll see, there is one block for f, there's a loop from ht back to itself through a delay. So this is black was nothing but a delay of one time step. Means what, values goes from t and it is used back at t minus 1. Sorry, t plus 1, not t minus 1. So this value is again used to this, so that is same thing. So here suppose we generate a ht, now I'll use it again. So ht is here. Okay, this t is again I'm using here t plus 1 is formed, then again it will be t plus 1 here, again it is used, so it will be t plus 2, it will change on like that. Okay, it's just like that. Oh, uh, okay. Then this is a compact and looks like an actual real-time system. Why real-time system? Because same delay is used and same thing is used for next step again and repeat in loop. So you expand the loop into copies. ht minus 1 goes to ht, then goes to t plus 1. Same as t1 xt minus 1 to t plus 1. So you're just adding one inside this bracket. Like that's it. Each copy is the same computation with shared parameters. What is the shared parameters? Theta over here and f over here. Okay. Parameters is f, but same computation is same f everywhere and same parameter, same theta everywhere. Now we are using unfolding graphs that depends on sequence. So the function g or gt. So this is like that. Okay. G of t. I have you see, I have put the diagram also. Whole history new equation. 10 point, I place the equation itself, because sometimes writing this like this will confuse you, so I have pasted it. So here this is the actual what to say, without unfolding how the system look like. It has to say, see, this is the state at time t is a function of the entire past. So state at time t is a function of entire, this is the entire past, like t minus 1, t minus 2, so on, 2 1 and all. It's just like that. So instead of writing like this complete entire past, what you are doing, but instead of learning a separate complicated function gt, so g of t into this whole thing, why don't we just unfold it? By unfolding it, it will allow us to factor into what, into this. So see, f of ht minus 1. This whole thing can be written as what, f of ht. So h of t is equal to, h of t is still the same. Instead of this g and the entire past, we can simply write it as f of ht minus 1 comma xt theta. That's it. So now what is happening? So gt is implemented as repeated application of the same f, that is function. Now we have two big advantages of that text list. Ignore this. This is the text which I had given for the AI. Okay, so whenever I talk about AI, I have to talk about this AI platform. I'm just trying to help you guys. So it's not like promotion. Okay, it's like trying to help you so that you can use this AI tool and allow some use a AI tool and make good notes and all. It's very good for you. It's like so many things are there, but yeah, you have to take subscription. That is this one. I'm already using this. See, you can see here at your plan. I have used it many times and different accounts. This is a second account with 30 credits left. This means I have used it a lot and made these notes. All these notes, all this explanation, where did it come from? From here itself. Okay, and see, it's easily I can download this PDF. If you see here, whatever is it, see, it's a feature. I can upload any type of thing. Universal document, upload any type of images, document, doc format, etc., etc. Here I can download it into whatever I have. I can easily download. So if I click here, and it will show me to see copy or PDF or Word, and if it, or else I have to spend 4 credits to download visuals. So it will give me images type of thing with some explanations. Very useful. Okay, advantage one, fixed interface, variable length. No matter the sequence, the model always uses the same step rule. So sequence is that what this ht minus 1 or and all, that is nothing but the sequence. So the input size of the transition are the ht minus 1 comma xt. So you can see this sequence too much is there, right? X1 x2 so on up to t minus 1 up to t. So it is a, so no matter what it is, so fixed interface variable, and that is ht minus 1 comma xt. You don't need a new architecture for different t. Advantage to parameter sharing across time. Same function f and same transition function f and same parameter theta at every time step. This gives generalization to longer sequence than training, fewer parameters, better statistical efficiency. Important intuition, very deep computational graph. The book hits this hard. 1D convolution shares parameter but is shallow. I will look into the textbook if some say this was also covered. Is anything missing? So, oh, this is the same thing which you are already replacing s with h, and this is the equation which we already covered. After this equation we don't have much anything, we just have to see this once and we'll move on. So see, 1D convolution share parameter but is shallow. Rather than sharing creates a graph that can be very deep in time. So this is 1D convolution, it comes under convolution from chapter 4. We have 1D and 2D. This is grid like structure, okay? Process rate and grid like. One more key point from your okay, what is it? Except HT is a loss summary. Because input history length grows with t, but time t, but HT is fixed size like that. So it must forget something unless it's designed to store almost everything. So if you see, it's like brain memory type. If you want to add new data, something you have to forget. So what you should walk away with that was so complete overview. RNN recurrence equation with shared parameters. It is a recurrent neural network which is a recurrence equation with shared parameters. Unfolding is nothing but turn the loop into a chain for t steps, t number of steps. Same parameter theta is used at every time step, and same transition function f is used at every step. Unfolded graph makes forward flow plus backward flow explicit. HT is nothing but models learn memory of the past. Models learn memory of the past. So whatever is happening in the past, that will be remembered in HT. If you talk about HT plus one, it will be remembering everything, including HT. That is about unfolding, guys. We'll see in the next.